Hello, my name is Akshay Tangsale and you're watching the pre-lecture video for week 3 of Material Energy Balances unit. Today I will recap what was covered in week 2, give you some hints about the key take-home messages from week 2, and then look forward to what is coming up in week 3. So in week 2 we started off by looking at fluid pressures and hydrostatic pressures. Hydrostatic pressure is the pressure created by a height of the fluid column at the base of a container. We looked at pressure measurements using manometers. In particular, we looked at U-shaped manometer, and there were 3 types of U-shaped manometers that we looked at, and the governing equation for those manometers. We also looked at temperature measurement, and this was only theory part, which showed measurement using thermometers, pyrometers, and thermocouples. We then moved on to chapter 4 and talked about the types of processes. We took some examples of these processes, in particular looking at batch process, semi-batch process, and continuous process, and also differentiating between continuous process and transient process. Mind you, all batch and semi-batch processes are transient by nature, whereas continuous process can both be transient and steady state. We then looked at general balance equation, which we can use for any balancing. General balance equation is input plus generation minus output minus consumption is equal to accumulation. This balance equation is always true when we apply for material balance as well as energy balance. However, we can make some simplifications when it comes to balancing certain problems. In taking an example of total mass cannot be generated and it cannot be consumed. Therefore, the balance equation reduces to input minus output equal to accumulation. And if we assume steady state, then accumulation is also zero, so input is equal to output. In other words, we can say total mass is always conserved. However, when it comes to component mass balance, it may or may not be conserved. In a reactive system, mass of one component gets reacted to make another component. Therefore, a mass of a component in a reactive system is not conserved. However, if you are dealing with a non-reactive mass balance, then mass of a component is also conserved. Then we looked at process flow diagram, and I will talk about more in the next slide. We also deal with degrees of freedom. In a nutshell, degrees of freedom is the allowable information given the number of unknowns. Degrees of freedom we can simply define as the number of variables minus the number of independent equations. These equations can come from mass balance equation, process specification like yield, recovery, or selectivity, or it can come from physical properties like density, molecular weight, or thermodynamic properties like equilibrium of a system or heat capacity of a system. So let's look at the key take-home message from week 2, which was process flow diagram. I've said this a few times in the lectures that process flow diagram is probably the single most important thing if you want to solve a material balance problem. More often than not, if you get the process flow diagram correct, you will also get the solution correct. So how do we get the process flow diagram correct in the first place? So we always start off by selecting a right basis for writing our process flow diagram or drawing a process flow diagram. Most often, a process, when it is defined, contains a basis for the calculation, such as feed stream flow rate or a product flow stream flow rate. So we can choose the basis given in the problem. If the basis is not given, then the choice is ours, and If mole composition is given, then we can choose 100 mole basis. If mass composition is given, we can choose 100 kilogram as our basis. Then we draw the units, which are boxes, and then the streams are drawn as arrows. These arrows are then labeled with the process variables. The known variables like mass flow rate or composition should be labeled along with any other process variable like temperature and pressure, which are relevant for energy balances, but it's a good habit to have right from the start. All the unknown variables must be labeled, and care must be taken to name the variables according to the units that are desirable in the problem, such as if a question asks you to calculate total mass flow rate of a product stream, then you would give a variable of mass flow rate for the product. If a mass composition is asked, you would label mass composition. If a mole composition is asked, you would label mole composition. Also write all the process specifications that are known to you, such as recovery, yield, or purity of a product stream. Remember, when you're writing composition of any given stream, you have n number of variables if you have n number of components. For example, if you have a 3-component system, you can write total mass or mole and 2 variables for 2 components. The third one would be 1 minus of the other 2. Therefore, choose the basis according to what the question is asking. If the fractions are known, then you write the total mole or mass flow rate and n minus 1 fractions. If the fractions are not known, then you write n mole flow rates or mass flow rates for each component. So let's look at what is coming up in week 3. So in week 3, we continue our journey in chapter 4, and after looking at the single unit operations in week 2, we look at multi-unit operations in week 3. In particular, we will look at recycle, bypass, and purge systems, and then move on to do balance on a reactive system. So when we come to reactive balances, first we will define some new terms like fractional conversion, yield, and selectivities. It's important to understand the definitions of these because these equations will not be given in your tests or exams. We will look at 3 types of balances: molecular balance, extent of reaction balance, and atomic balance. We will talk about which balance is most suitable in which scenario, but upfront I would like to tell you that molecular balances is not recommended. You should either look at extent of reaction calculation or atomic balances. Then we will look at a special case of reactions, which is the combustion reaction. It's very important in energy generation, so we pay special attention to this type of reaction. Finally, I would like to talk to you about the homework reading for week 3. So in preparation for the lectures next week, please read sections 4.4 to section 4.8 in Felton-Rosa textbook and pay attention to examples 4.4-2 and 4.7-3. Thank you for listening to me, and I will see you in the lectures next week. Bye for now.